right. Our next speaker is Zhao. Is assistant professor at IIS University and a PI of the Mars Lab. His research interests are multimodal machine learning, autonomous driving, and animal learning. He was a research scientist at Bimanual from 2019 to 2020, and before that, he got a PhD degree at MIT in 2019 with Professor Antonio Taroba. Before MIT, he received his bachelor degree from Zhao University. With that, let's welcome.
Thanks for the introduction. Hi, everyone. I'm Hang, assistant professor at Tsinghua University, principal investigator at the Shanghai Teaching Institute, and I also have co-founded our startup called Galaxy. And today's topic is about towards athletic intelligence. The legged locomotion has been there for a very long time, like 40 years ago. From 40 years ago, Boston Dynamics has built robots with single leg, 2 legs, 4 legs. Right? When I was at MIT like 10 years ago, I was really impressed by the project by Zhao team. I was also in Zhao team at the time. As you can see, the robot is really agile, jumping over the high obstacles. But you can see the tricks here, right? We paint the obstacles in pink, or else it does not understand it. And since that we have achieved such agility 10 years ago, but why don't we still select robots around our daily lives, jumping around? Behind the scene, we'll see how the engineers achieve this goal. This is what the engineers were doing in order to achieve this demo. Two things to notice here. The first thing is that they are planning footsteps for the robots to make sure that each footstep is placed at the right position. And second, you notice that it uses LiDAR sensors. So these are the two aspects of like general robots, right? One is perception, the other one is motion planning. The motion planning and control is a bigger problem because these optimization-based methods is not possible to solve very complex environments in real time. So we need to plan beforehand. The optimization usually takes 10 or 10 minutes or even to an hour. And the second problem is that they have perception superpower. They pre-map the environment and then use a depth sensor or LiDAR sensors to understand where it is right now and to know whether it is blocked, if there are obstacles blocking it or not. So in order to make the robots more generalizable across different environments, that's why people today are doing perceptive reinforcement learning locomotion. Right? However, the demos from reinforcement learning locomotion looks less capable than NPCs. So it is really important for us to show that how perceptive RL locomotion makes traditionally hard control problems easy. I think all these changes, these milestones happens over the last 1 or 2 years. And so today, in today's talk, I will share some research works in my group over the last 2 years. We started from robot parkour learning. Parkour is a really exemplary task to demonstrate the advanced capabilities of perceptive locomotion. Because this is a task that can be easy and can be hard, And it's very good. It's very good for us to show, to give a very impressive demo. The overall feedback system is very simple. Our robot can be a humanoid or a quadruped. It uses depth sensors to understand the environment, the 3D environment. And our policy takes these exteroception, including depth, odometry, and also proprioception, including like the joint angles or angular speed of the joints, and outputs the expected joint angles for each motor of the robot. And then a PD controller will take the expected joint angles and some proprioception information, and finally outputs the torques. The PD controller operates at around like 500 to 1000 hertz. So let's go step by step. Let's first talk about how to make the robot to walk robustly. Walking looks like a very easy task for robots. There are prior works, for example, incorporating some motion priors or set like a human rule, like feet at a time, like basically saying when the robot is walking or running, how much of a amount of time the robot's feet should be raising in the air so that it can move forward. But these rule-based or prior-based methods, we find them to be to not be too general. So we solve this problem in terms of the simulator. What we do is we add fractal noise in the simulators, more specifically on the ground, to make sure that when the robot is walking in a simulator, it can unconsciously meet some invisible obstacles on the ground. And then, just like humans, we do not always look at the ground when we are walking. We look to the front, right? We don't look on the ground. So in order to avoid these small, tiny obstacles on the ground, we need to raise our feet. And that will help the robots to work more robustly. And this is our first indoor walking test. This is the very first time that we deploy our policy on a robot. And it seems that the robot has a really good performance in walking around in our office. Looks like it's patrol around and see if everybody is working conscientiously in office. And finally, back to his stage. Okay, and then we take it outdoors. Outdoor running and outdoor walking on different kinds of grounds. Okay, after it can walk robustly, the next step is add some challenging terrains so that the robot can perform parkour. For quadruped, we ask the robot to do climbing, leaping, crawling, tilting. And for the humanoid, we ask it to jumping up and down, steering up and down, cross like slopes, hurdles, discrete or wavy grounds, and many, many different kinds of challenging terrains. And then we train the policy. When training the policy, we find that when the terrain is too challenging, the policy is a little bit reluctant to learn. So what can we do to help it learn better? The answer is curriculum learning. The idea for curriculum learning for robot parkour is that we do not at the very beginning, we do not put hard obstacles in front of the robots. Instead, we put some virtual obstacles. As we show here, these virtual blue boxes are the virtual obstacles. These soft dynamics constraints basically says that, okay, the robot can penetrate into the obstacles. However, whenever it penetrates into the obstacle, it will be penalized in terms of reward. More specifically, we put points, we sample points on the robot's body. And whenever these points penetrate into the obstacles, and we'll count the number and the penetration depth. And we'll use the negative of the number of points plus the penetration depth as the reward. And we find that the robot can gradually learn how to avoid these virtual obstacles and finally obey the physical rules. This is a video of the robot learning over time. From iteration 0, it will cross these virtual obstacles, and gradually it will learn to avoid these virtual obstacles. And finally, we will fine-tune with hard dynamic constraints, basically the hard real obstacles. And of course, if you want the robot to be very robust to various kinds of terrains, it's better to chain these challenging terrains together and train the policies. And finally, we incorporate perception into the system by distillation. This is very similar to other previous works. It was trained with oracle perception, and then we replace it with real depth sensing. And this is what we can achieve by directly deploying the policy into the real robot. This is the quadruped example and the humanoid example. And what is interesting is that we find that there are a lot of emerging behaviors after we deploy the policy on a robot. For example, for the quadruped, it learns how to retry in order to get onto a very high stage. Because the policy is a recurrent neural network, so it will remember what it has experienced before, just now, and then try to perform a better policy, a better output, a better action. This is similar for humanoids, but differently, the humanoids learn some other skills. The humanoid learns to swing its arms up when it tries to cross a very large gap, or when it tries to step onto a high stage. Then, with this parkour policy, we can do something else. For example, humanoid teleoperation is a free lunch. What we do is we develop a teleoperation device, as shown here, only for the upper limbs, and then we will override the upper limb motions for the humanoid robots. And then we will combine the upper the upper limbs and the lower legs motions together. Then we can play badminton with the humanoid robot. It's actually humans playing badminton with humans. Okay, and then when we are working on humanoid robots, we're asking a question: what's the difference of a bipedal robot and a humanoid robot? Right? Bipedal robot is that it uses 2 feet to interact with the ground, but we humanoid robots has upper limbs, has upper bodies. So theoretically, like it can use all body parts to interact with the world. We want it to learn like human-like motions or interactions with the complex environments, as we shown on the right-hand side. Right? It should learn to crawl. It should learn how to sit on a stone. Then it raises another series of challenging technical questions. That is, if we try to dissect the problem into smaller pieces, and we'll meet an exponentially growing contact tree for the contact-rich problems. And it is almost impossible to solve this problem with NPCs. Right? There are just so many cases that you need to discuss with MPC. So this is a perfect problem for perceptive reinforcement learning. And as you may know, like actually over the past year, this problem is super hot, humanoid full body control, right? An easier solution is that on the right-hand side is called predefined motions. You can predefine a motion and train the policy and let it to track the motion over time. And a more challenging, a more desired way is motion instruction following. Basically, we send the full body motion instruction, and it can be an arbitrary motion, and we'll let the robot to track this complex motion. So our goal is to train such a policy. At the training time, we try to get a motion data set and train the policy. And the data set is composed of very complex, diverse set of motions, and we let the policy to learn to track it. And at the inference time, we can input arbitrary motions, and the robot can perform this specific arbitrary motion. So what we do is we started from a popular motion data set called AMOS dataset and train our policy with a PPO. Let's see what we got. On the right-hand side is our motion command. It's basically the motion in the AMOS dataset. And on the left-hand side is the result of our policy. As you can see, the policy refuses to knee down. So why does that happen? We debugged it for a long time, and we found that the dataset is to blame. Basically, in the AMOS dataset, the distribution of certain specs are quite biased. For example, most of the base height of the humans in this dataset is around like 0.8 meters. And the base orientations are always up straight. So that's why the robot refuses to knee down. It refuses to crawl on the ground. So it's time to build our own dataset. First, we manually select some interesting motions and actions in the AMOS dataset. And additionally, we crawl a lot of videos from the internet and try to recover the human motions in it. And we select those interesting motions like breakdance, like kung fu in it. And then curate a new data set. With this new data set, we are finally able to train a policy that the robot is willing to stay on the ground. Okay, and then let's talk about the deployment. For onboard deployment, the policy is directly deployed on the robot itself. And at the same time, we have an additional laptop that's sending high-level commands at low frequency with latency. And the policy itself will deal with this latency and finally perform the action. And here are some ground whole body motion demos like breakdance, Japanese jiu-jitsu, getting up from the ground, no matter it is facing up or facing down. Cool. And the next works that I would like to talk about is removing the perception superpower and use RGB vision for locomotion. There are several motivations for using RGB vision for locomotion. The first thing is that depth is actually a terrible sensor and it's evolving over time. Somebody uses LiDAR, somebody uses depth sensors, and it is not robust to the complex environments like transparent objects or reflective objects. And the second motivation is more important, is that the future robots, we hope that they're just like human beings. They understand the semantics, the high-level semantics of the environment, and also performs low-level control. However, if you use depth sensors, the only thing you can do is to do low-level control. Because most of the semantics, we get most of the semantics from RGB vision. So thanks to the advances in computer vision area, Gaussian splatting technology, we're able to perform some real to sim to real technology. The idea is basically that we first use vision to reconstruct the 3D world and put it into the simulator, and then we train the RL policy in the simulator and finally deploy back to the real world. More specifically, what we are doing is first, we create a digital twin of a neural environment with Gaussian splatting, with a geometric aware Gaussian splatting. More specifically, this Gaussian splatting technology, it tries to find the correspondence between triangular mesh and a Gaussian ball. And in that way, we are able to, we have the geometry for each Gaussian ball. And then we put the whole reconstruction result into the simulator. And during reinforcement learning training, what we do is the reinforcement learning policy, the simulator will replace the rendering function of the simulator with our Gaussian splatting novel view synthesis function. So basically, the Gaussian splatting runs at 100 Hertz to render RGB images for the robot, and the robot will learn its control policy in the simulator. And we find this approach to be very effective.
Within scene 1, the red code was randomly placed in one of 3 regions.
And we task it with the task setup is a little bit simple here. We ask the robot to catch the cones of different colors, either green or red or blue. And the robot learns the high-level semantics and also learns the navigation and the locomotion, everything by itself. So this is basically a one network for all solution. Okay, due to limited of time. Yeah, the next work I would like to talk about is multitask reinforcement learning. Multitask reinforcement learning is empirically very hard. In our parkour project, we found that whenever the terrain is becomes harder, and then the policy refuses to learn. When the policy is faced with multiple tasks, it's even harder for it to learn. So what we typically do is that it learns each task individually, even with some curricular learning techniques. And finally, we distill multiple skills into one policy. But here our goal is to learn learn to master all the terrains and gates in one single policy. And we take the approach that is popular in large language models, mixture of experts policy. And we find it to be very effective in solving all kinds of the combinations of terrains and gates, including like here, like bar, slope, pit, baffle, with quadrupedal gates and bipedal gates. Here's a quick demo of this single policy can do. It conquers all kinds of terrains. And we also have a command to ask it to change its gates from quadrupedal to bipedal. Yeah, and we find that it has better performance in terms of multitask performance over previous works, and across all the terrains it performs better. That's pretty impressive, actually, and we think that it might has avoided gradient conflicts during the training for multiple skills. Next, we have also observed that the different experts is correlated with different kinds of terrains and different kinds of gates. And we do a simple t-SNE clustering on the expert selection, and we found that okay, on the left cluster is a quadrupedal cluster, and the right cluster is a bipedal cluster. So each expert specializes. Okay, given that we have this bunch of experts, and we can do some very interesting things. For example, we can do skill decomposition and composition. It means that for each task, we can decompose it into multiple skills, and then we recompose these skills together, to achieve a new task. For example, here what we are doing is that we are combining a balancing expert and a crossing expert together. We only activate these two experts in the network. And then compose them together. And now it looks like it gets a dribbling gate. And we directly deploy this dribbling gate in the real world, and it can dribble a ball. And it also learns quickly adapting to new gates. For example, use 3 legs to walk. In order to learn this gate, it only takes 2 or 3 minutes to learn to walk like that. Okay, that's everything that I would like to share today. And I think the future of athletic intelligence is really bright, and there are still a lot of work to do. For example, agility and force control, and whole body control learning for humanoids, and multi-robot competition and collaboration in interesting and competitive events and environments. And finally, I would like to thank my students, the leading authors. Ziwen is the first author for the 3 papers, parkour and whole body learning. And Shaoting, Lingzhan, Baijun are the authors for this real to sim to real paper. And Renhan is the author for the MOE paper. Thank you.
So I have a random question, like how large scale is the model for training some experts? So like
how large is the data set or? Oh, the model size is really small. It's several million parameters. Yeah. Yeah, I think I think the reason that we use MOEs here is slightly different from large language models. I think for large language models is more like to basically I think here what we are doing is in order to deal with the multitasking issue. But for large language models, maybe I think it's more they want different parameters to specialize in different capabilities for these really complex large language models. Yeah, but here I think it's what the problem we are solving is mostly the training process, the training dynamics.
All right, let's thank the speaker again. We'll go on break, and then we'll be back for REI's talk and our panel discussion. Goodbye.